All right, so how do we find how many protons? You just look at the atomic number, right? So 20, which I'll go ahead and finish the symbol by putting a 20 there. So I've got 20 protons. How do I find number of neutrons?
Subtract.
Yeah, the mass number, which is 42, minus the atomic number 20. So 42 minus 20 would be 22 neutrons. And how many electrons?
20.
No?
18.
18, because it's got a 2 plus charge here.
Yep.
Okay. So 2 plus means you subtract 2. 18 electrons. The charge is always protons minus electrons. So 20 minus 18 would be positive 2. 20, 22, 18. Any questions about that? No? Okay, good. Let me go back to where we were. Now, the book also discusses something which is rather important, but I'm going to delay going into. In chapter 4, let me go back here. There is figure 4.14. This is page 114. And this talks about the standard charge of the elements. How the elements in group 1 are +1, the elements in group 2 are +2, 3, these top ones are +3. That's vitally important, but we don't really understand why yet. And so I don't like to talk about this until we get a little bit further in the class, chapter 5. And we're going from 4 to 9, 10, and then back to 5. So don't worry about this. And also don't worry for right now about writing these ionization equations. I mean, it doesn't hurt to practice them because we will need to do that later. But it's not something that I think I took all of those off the homework. So you won't see those written anytime soon. So just wanted to make that note. So we're not totally in the dark on something. Okay, the mass of an atom. Now, as I'd mentioned, the mass of an atom mostly comes from its nucleus because that's where the protons and neutrons are, and the protons and neutrons are about 1,800 times heavier than an electron. And the issue is, whenever you go ahead and you are measuring out the sample of an element, how many atoms do you have in a typical sample? If it's something you can see, we're talking billions upon billions of atoms. And it's almost always going to contain more than one isotope. There are certain elements, like aluminum, that only contain one isotope typically. But most elements, in fact, come in multiple isotopes. And we'll be doing the calculations for those in just a moment. So we would like to know what the average mass of an element is. Okay, and that's going to be called the atomic weight of an element. Now, the unit that we will use for these, and by the way, this calculation that we're going to do for doing this is the exact same way that I calculate your grade. It's what's called a weighted average. And we'll see how that's done in just a second. The units we're going to use for this are called AMUs, or atomic mass units. In Chem 130, I think the book uses the letter U instead, but AMU. And it's an incredibly small unit of mass. So when we talk about an AMU, it's 1.66 times 10 to the minus 24 grams. You don't need to know that by memory, okay? Don't worry about memorizing that equation. So for example, a single helium atom is 4.003 AMU. These masses are all on the periodic table. So I said just a second ago, helium was 4.003 AMUs. That's the mass of a single helium atom. So on average, if you average over all the isotopes, okay? Aluminum, 26.98 AMU. Calcium, 40.08 AMU. For those of you that have had some chemistry, what else is that number going to represent? Anyone know? It's the number of grams of the element in what we call a mole, okay? The mole is very, very central in chemistry. In fact, I call that thing mole mastery because all the calculations that we're going to do from there on out when we use mole mastery are related to moles. So we'll get to dealing with measuring these things in grams per moles later. But for right now, we're just going to say these are the mass of an individual single atom in AMUs, okay? Single atom. Okay, I need to have a periodic table open somewhere else too, or I'm going to keep going back and forth. Okay. Now, where do those values come from? Well, they're coming from the mass of each individual isotope plus the percent abundance of that isotope in nature. So there's two things that we need to know. Percent abundance is just, if I look at all atoms of that particular element in nature, what percent of them are a particular isotope? And this is best done with an example. Now, these are the most tedious problems we do all semester. They're not hard, but they're just tedious. So there are 3 isotopes of potassium. Potassium 39, potassium 40, potassium 41. Now, if we wanted to finish the symbol, what would all 3 of these have in common? They would all be down here. They would have 19, if you look on the periodic table. They all have 19 protons. I'm not quite sure. Oh, no periodic table there either. Well, I'll have to look later, but I'm quite sure it's 19. And most of the atoms of potassium that are out there, so if you ate a banana, you had some potassium today, 93% of them roughly are this isotope, the most common one, potassium 39. But mixed in are also potassium 40 and potassium 41. Potassium 40 is much, much less frequent than potassium 41 and potassium 39. So I want to calculate the average mass. In other words, I want to be able to get this number right here. I want to be able to show where that comes from. Okay. And my data might be a little bit off on this, so it might not round exactly correctly, but it should be close enough. All right, so we just do a weighted average. It's very simple. It's just going to be, we take each isotope and you take its mass times its percent abundance. Okay. So the atomic mass, or atomic weight, it will be the mass times the percent abundance. And the percent abundance needs to be converted to a decimal. So what is 93.2581 as a decimal? All you do is move the decimal 2 to the left, right? So 93.2581% is 0.932581. Times 38.963707 AMUs, but I'm going to run out of space if I put the units. So I'm going to be bad and not write the units. Percent abundance for the next one is going to be, what will this number be here? 0 point.
Maybe 11 or 71.
So no, 0, 0, 0, 0, 1171. Be very careful. Decimal moves 2 places to the left when you go from a percent to a decimal. Okay, and that will be times 39.6, excuse me, 96, 3, 9, 9 plus 0.067302 times 40.961826. Now this leaves us with a substantial significant digit problem. Okay, again, this was potassium 39. This was potassium 40. This was potassium 41. And so it's good because it'll help us to practice significant digits. You have a combination of multiplication and addition. So we do, of course, the multiplication first, and you follow multiplication rules. So let's do that. So I've got 0.932581. And I want you to be doing this with me. Don't just wait, because you don't want to make these mistakes if this question's on the exam. 38.963707. 38.963707. Good. And so we count the number of significant digits. The one on the left has 6 significant digits. The one on the right has more than 6. So it's going to be 6 significant digits here. 36.3368. Usually best to keep one additional digit, but for this problem, I'm not going to bother with that. I think it would just confuse things. Okay, the next one, 0.00001171 times 39.963999. And I'm getting a number in scientific notation. I don't want it in scientific notation. So I'm going to rewrite that as regular, 0.000. How many significant digits can I have?
4.
4, good. So this will be 4680. Plus the last one, 0.067302 times 40.961826. And how many significant digits on this one?
5.
5. Good. 2.7568. Good. The next rule is we need to, since it's addition, what do? We look and we identify the last decimal place. and we want the least precise of those. So it's not how many significant digits. Some of you are still doing that, and you're counting how many significant digits. That only matters for multiplication and division. Okay, so this ends in what place is that? The 8 is in which decimal place?
10,000.
10,000's good. Yeah, I'm noticing a lot of people still don't know their decimal places. That's a problem. You got to know your decimal places. This one I'm not going to bother because it's clearly beyond the 10,000s, right? And this is also the
10,000.
So when I add these, I'm going to need to round to the 10,000s. And so that's what I'll do. So 36.3368 plus 0.0004680 plus 2.7568. And this gives me 39.0941. Which is close to what the value says on the periodic table. And the units of all of these were atomic mass units, AMUs. Okay, so that's the average mass of a potassium. Any questions on how I did that? No? Okay. Let's try one more. Chlorine has only 2 naturally occurring isotopes. The atomic weight of chlorine 35 is 34.96885, and its percent abundance is 75.53%. What's the atomic weight of the other isotope? In order to do this, what piece of information do I need that's not in the problem? There's actually 2. There's 2 other values I need that are not in the problem to find this. Look at the equation we had here. So first we would have, if we wrote it out in words, it would be atomic weight would be the percent abundance of chlorine 35 times the mass of chlorine 35 plus percent of chlorine 37 times the mass of chlorine 37. Which one of these is the unknown that you're being asked for?
The weight.
The mass of chlorine 37. This is the unknown. Okay, that's the unknown. So I could have written weight, sorry. Yeah. In fact, if that makes it less confusing, you can write weight there instead. But really it is a mass. It's the atomic weight. Okay, good. So what do we know? I'm giving you the atomic weight of chlorine 35. That's right there. I'm giving you its percent abundance as a decimal. Do we know the percent abundance of chlorine 37? Or can we find it out? I always get kind of a little frustrated when people don't know how to do this. This should be easy.
Subtract the percent abundance from 100
Exactly.
for the 35.
Yeah, because there's only 2. Now there's only 2, they have to add up to 100%, right? So percent of chlorine 35 plus percent of chlorine 37 must add up to 100%. And so therefore, the percent of chlorine 37 is 100% minus 75.53%, which is 24.47%. The percents have to add up to 100%. Now we have the percent. We also need the atomic weight of chlorine, the average one. And so given no other information, what we'd have to do is we'd have to use this number right here, 35.45. Okay. Now that's going to limit us on significant digits, right, rather substantially, but that'll be okay for this problem. So 35.45. But make a note that that number comes from the periodic table for chlorine.
It's going to be on the next page.
Yeah, it's the
Oh, I'm
next
sorry.
page.
Yeah, why am I even writing that? Thank you. I'm like, why am I doing that? That makes no sense. All right, 35.45. AMUs. So the percent of chlorine as a fraction, as a decimal, is 0.7553. And the weight of that is 34.885 plus 0. I don't even need a parenthesis there, 0.2447. And since it's unknown, we'll call it X. Okay, so let's call this X. So we just have to solve. So let's just do the multiplication real quick. 0.7553 times 34.96885. And again, I'm just writing this all out so we can keep track of our sig digs. So 26.41. 0.2447x equals 36.45 or 35.45. We subtract. And we have to round to what decimal place? We have to round to the
10,000s.
to the hundredths, right? Hundredths when you subtract. So this would be 9.04. This is still in AMUs. Equals 0.2447x. So x would be 36.9. Yeah. And so here you see where, having limited significant digits can really hurt, because I ended up with only 3 significant digits when I did this subtraction. So then when I did this division, I still end up with only 3, whereas this one I have, what is that, 7 significant digits? So as I said, having one bad measurement really weakens everything. What I should have done here is looked, well, no, I'd have to look these percents up to an even larger decimal place. And sometimes we just don't have them available. Sometimes they're just not out there. So this was the best we could do with the data that we have. Okay, so again, the exam covers up to here, chapters 1 through 4. Chapter 1, you were supposed to read on your own. It's not all that difficult. I think it just reviews the scientific method and some recommended study methods for chemistry, which are very good. I like what they're talking about there, but I leave that to you to read. There's no reason I need to lecture on it. And then I'm going to skip to chapter 9, and this material from here on out will be on the second exam. Okay, so before we get into the electrons, let's talk about light here. So this term electromagnetic radiation describes a very broad band of everything that we would normally call light. And it includes what we call visible light, which you can see. So that's radiant energy, like visible light, but also things you can't see, like X-rays and radio waves. Now, when we talk about electromagnetic radiation, it can be described in two distinct ways. And this is something that it just blows the mind, because it's not something you can really visualize or even see mentally. It's like being two things at once. It's like being a cookie and being love, two totally disparate things. And that's what it is. It's like an idea and something else. So light or electromagnetic radiation can be described as waves. It has the properties of waves, which can be characterized by wavelengths. That's the distance from one peak of one wave to the peak of another wave. And we can also describe light as particles called photons. In crazy ways, light has properties of both things at the same time. Now, an alternative to measuring wavelength is frequency. Let me just show you wavelength real quick. So wavelength, identified by the Greek letter lambda, is just the distance from the height of one wave to the height of the other. Technically, it doesn't have to be the top point. It could be the bottom points, the troughs, or it could be wherever the pattern starts to repeat. As you probably know from math, this kind of a function right here is called a periodic function. It's a function that repeats itself over and over and over and over, theoretically out to infinity. Okay. So you can measure wavelengths, or instead of measuring wavelengths, you can measure frequency of waves, which is the number of waves that you're counting in a given period of time. Think about it as if you're standing on a pier and you're counting each time the top of a wave comes by you in a certain amount of time. That is what the frequency would be. So for example, let's say we're looking at waves going through some kind of a gate, and you have special equipment that can detect this. And so say we went through 445 waves, the peaks of 445 of them in a second. The frequency would be 445 per second. So what does -1 power mean? It means the unit is in the denominator. Okay, it's in the denominator. So even though we don't write it here, what word is implied? It's 445, actually two words, 445 waves per second.
Okay.
Yeah, so even though we don't see the word waves, because that's sometimes confusing, we usually will replace that per second with a unit called a hertz. So I'm sure if you've seen well, I don't know that you do these days, but on older cars, you used to have frequency dials. Oh, you still do when you're dialing a radio station, right? And it says megahertz or kilohertz. That is the wavelength that you're using for radio waves to pick up on a radio frequency. Frequency and wavelength are inversely proportional, which means that if you double one, the other is halved. Okay? So if one goes up, the other goes down by the same proportion. Frequency times 10, wavelength divide by 10. The mathematical relationship between wavelength and frequency is as follows. The frequency will always equal the speed of light divided by the wavelength. Okay. Or you could write this as frequency times wavelength equals speed of light. That would be an equivalent form of writing this. The speed of light does not need to be memorized. If you need it, I will give it to you. Other books also have it to more than 3 significant digits. All right, so this is kind of summarizing the two. So imagine that you're sitting here counting waves that are coming by you, and these waves are moving left to right. I know this looks like a distance, but they're saying this is a second of counting waves. So if you count this in a second, it's 4 hertz. there's 4 waves, 1, 2, 3, 4. And this would be just the beginning of the 5th one. So we don't quite get 5, but 4. Then we would get here, what are we doing? The frequency is what's happening to the frequency when I go from here to here, as specifically as possible. The frequency is
Doubled.
doubling. Good, very good. It's doubled. So what's happening to the wavelength? If the frequency is doubling, the wavelength is
Shorter.
by how much?
Twice.
1/2.
1/2. Yeah, it's half the length. Good. And then the same thing here. If you double the frequency again, the wavelength gets a half shorter. So that's the nature of inverse proportionality. If you multiply the frequency by something, you divide the wavelength by that same number. So there's always that relationship between them. Okay. Now, there is a correspondence between the energy of a photon of light, that's how we're thinking of light as a particle, and its frequency, using this very vital equation, which I don't think I'm actually going to make use of this semester. And that is that the energy of a photon is h, which is called Planck's constant, times the frequency. And this is the Greek letter nu, by the way. Looks like a V, but it's the Greek letter nu. Planck's constant is the smallest number we'll probably ever encounter, 6.626 times 10 to the minus 34 joules times seconds. Okay, so the greater the frequency, higher energy photons, because energy and frequency are directly proportional, right? H can't change, but if you make this number twice as big, this number has to be twice as big. Energy and wavelength would be inversely proportional. And let's prove that by coming up with a formula. How would we do that? How would we come up with a formula that gives you E equals something times wavelength? You would just, very simple. A skill you need to be really good at is you're just rewriting the formula. So E equals Planck's constant times the frequency. And the frequency equals what? Up on the top, it equals the speed of light divided by the wavelength. So in other words, we could say that energy equals, oops. Planck's constant times the speed of light divided by the wavelength lambda. And the energy is in units of joules. These are typically going to be extremely small amounts for every photon. Every photon, for example, of red light is about 10 to the minus 19 joules. So very, very small amount.
Professor, in the
Yeah.
equation, it should be like you have energy. I don't know how to explain that. It should be nu the speed of light on divided by
Which one?
just right to the right a little bit. Yeah, right there.
Okay.
Yeah, because h is the Planck's constant.
Yes, h is Planck's constant, and nu is speed of light over wavelength. Okay. So that's the energy of a photon.
Okay.
Okay, good. So then what did we say the relationship was between energy and frequency? Are they directly or inversely proportional? They are directly proportional. If one increases, the other increases as well. And energy and wavelength are Inversely proportional. Oops. Is that correct? Ah, there we are. Good. Okay, so what we're going to do here is we will break the electromagnetic spectrum into several different regions. And you can do that again based on wavelength or frequency. The very longest wavelengths, which would be the smallest frequencies, are the radio waves. The very shortest wavelengths, or the greatest frequencies, are the gamma rays. And this is a diagram that shows the entire electromagnetic spectrum here. So we see again, if we're going from left to right, the wavelengths are getting larger, but the frequencies are getting smaller. If you go the other way, to the right to left, wavelengths are getting shorter, but the frequencies are getting larger. You do not need to memorize the spectrum at this point in time, okay? I'll leave that for physics. And nor do you really need to know any of these values, but these are just wavelengths in nanometers here. You'll notice out of this whole thing, the only light that we can visibly see is this very limited range right here, which is captured between ultraviolet light and infrared light. Has anyone ever memorized this sequence of colors? There's a way of doing that. Anyone know the acronym?
Roy G. Biv.
Roy G. Biv, good. And that would be going this way. That is, in other words, going from longest wavelength to shortest wavelength. So red, orange, yellow, green, blue, indigo, violet. Okay. So red is the longest wavelength, but the lowest energies, right? The longer the wavelength, the lower the energy. Violet is the shortest wavelength and the greatest energy. And what do we encounter as you go even shorter on the wavelength? You get into the ultraviolet. And we know ultraviolet light can be damaging to skin, right? This is one of the reasons we wear, what's it called? Sunscreen. And eventually, if too much exposure to ultraviolet light can lead to skin cancer. So it's something that we have to protect against. Anything further, and it gets even more dangerous. X-rays can cause damage to cells, which means, if you go and you take a dental X-ray, you always need to put on some kind of a shield to protect the rest of your body's tissues from the X-rays. Gamma rays have so much energy that they're incredibly damaging, and too much exposures to gamma rays can be fatal or can cause cancer to develop in time. So these guys are rather dangerous. Now, for people who freak out about radio waves are on this extreme end. And you'll notice visible light has a lot more energy than radio waves do. So if people are talking about your cell phone's going to give you brain cancer, no, it's not. The thoughts you're thinking might, I don't know, but no, it's too low in energy. Okay. Now, terminology becomes extremely important in this chapter because there's a lot of nuances between different words. Now, when scientists were first trying to really elucidate the structure of an atom, one of the more important theories that was developed ends up being wrong, but still has some very useful concepts in it that we use in our current model, is called the Bohr model. So not correct, but a good introduction to the atom. And in that model, we model the atom like a solar system, where the nucleus is at the heart, just like the sun would be at the heart of the solar system. And then the electrons would orbit the nucleus, just like planets orbit the sun. Okay. In circular orbits. Now, there's a number of reasons that doesn't work, but it appeared to work when it was first being developed. And because of certain aspects that appear to work, we're going to stay with their technology. I mean, with their terminology. Okay. So these orbits, which I'm putting in here just to say they're not really orbits, are going to be things called energy levels or shells. Either of these terms can be used equivalently. So if you imagine the nucleus being at the center of an atom, the first energy level would be like the orbit closest to the nucleus. That would be also called the first shell. Then there's another shell. So it would be in a solar system like saying Mercury is the first, and then the second would be Venus, and then the third would be Earth, right? So it's the same kind of an idea. And that's how you want to visualize it for now, until we can come up with a more thorough concept of this. Okay. Now, so that's the one thing we need to visualize is the farther the energy level is from the nucleus, the higher the energy of its electrons on average. Now, electrons can fill up these lower energy levels first. And then once they are full, they move to the next energy level. It's just like a room with people. You can only put so many people in a room. As we're going to find out, the first energy level can only hold 2 electrons, and then it's full. If you try to add a third electron, it has to go to the second level. The second level can hold up to 8 electrons. And we'll see how I'm coming up with these numbers as we go further. So assume that the electrons are filling up the way they're supposed to. So for a hydrogen atom with only 1 electron, that electron should go in the first shell. If they're following the rules, we say that the atom is in the ground state, meaning it's at its lowest energy level that we expect for that atom under those conditions. If we add energy to that atom, either through light or heating, the electrons will gain energy and can jump from one of the energy levels or shells to one of the shells further out. So in other words, if an electron is in the first shell, it could jump to the second shell, it could jump to the third shell, the fourth shell, etc. One that is further away. And when one or more electrons are further away from the nucleus than they normally would be, we would say that the atom is in an excited state. Again, this is all models. The reality of the situation is much more involved than this. Okay, so that's showing this procedure here. So if we imagine the photon looking like this is from a different book. This is a cool way of trying to show a photon because it's showing that it's a little particle of energy plus it's a wave. They don't look like that. They don't really look like anything. But that's, if we imagine that, and these are energy levels. When an atom absorbs a photon of energy, its electrons get excited to a higher shell or higher energy level. Now, there is a law of conservation of matter or energy. Remember, we had a law of conservation of mass. There's also a law of conservation of energy, which tells us that energy cannot be created or destroyed. It has to just be distributed. You have to move it around. So if you had to put energy in to get the electrons to jump, to excite them, energy must be released when the electron falls back into the ground state. So we call the absorbing of energy absorption. And when it falls back, we call it emission, because at the same time the electron falls back, it shoots off a photon of light. What kind of light? It depends on what energy levels they are. If this is energy level 1 and this is energy level 2, for example, it will always shoot off UV light. Anything that falls to the second level always shoots off visible light as a photon. And this is really the concept behind a lot of our lamps that we have out there. So for example, a halogen lamp or a fluorescent lamp, you know, those long tube lights, you're supplying energy as electricity. The electricity excites the electrons. And then when they fall back, they emit color. Same thing with a neon sign. A neon sign contains neon gas. You supply electricity. The electricity excites the electrons in the neon gas. And when the electrons fall back, they emit light. So it's a vitally important concept here that we have. So always the energy level or shell number goes up when you're absorbing energy, and it goes down when you're giving off energy. This is going to be the basis of a whole new type of physics called quantum mechanics. Okay. Everything that we do up until then, when we normally study physics, is called classical mechanics, things like Newton's laws, if you've studied physics at all, torques and angular momentums and all these other things. Okay. So as I said, this is called the Bohr model. It is not correct, but it is, but real matter, but light, but atoms behave very, very similar to this. So that's why we're going to just not throw it out. So, and this comes again from another book, and this is just showing that these are what? What do these circles represent?
The energy level.
Energy levels, or we could again call them shells, correct? The energy levels are the shells. And this is just showing the photons of light that are emitted whenever an electron falls back to a particular shell. So ultraviolet light is given off whenever something is falling to the first shell. Visible light is given off when it falls to the second shell, and infrared when it falls to the third. Okay. Now this is cool because if you take a given element and you look at the light that it's giving off through a prism, it will break it down into discrete wavelengths, and you can see what color bands are being given off. So for example, in hydrogen, we see 4 distinct colors. Now I'm going to continue to use these numbers for our energy levels. Sorry. Oh, that one didn't want to come out. Anyway. So energy level 1, thank you. We'll write n equals 1 for the lowest energy level, n equals 2. And theoretically, this goes to infinity, but we don't really see anything beyond about level 8 or 9 for most of our experience. Okay. So this is just showing you that if you have a tube and you hook that tube up to an electric current, so it will give the gas inside the tube energy. It shows how that will excite atoms. Okay, so this is a tube that has hydrogen. So if this is hydrogen and it goes through a slit and then through a prism, we will see a spectrum. We'll see light here at 410, 434 nanometers, 486 nanometers, and 656 nanometers. So 4 distinct points. What if the tube had mercury vapor? If it had mercury vapor, it would give a spectrum, but is it the same as hydrogen?
No.
And strontium as a vapor would also have its own spectrum. So you see, this is an extremely cool idea because it allows us to identify various atoms that are being given off by different elements. Like, for example, I'm sure you've heard people say such and such a star contains these elements in it. And you go, well, how in the world would we know what elements a certain star could have? I mean, we can't get anywhere near the star. But if you look at the light it's emitting, that gives us an idea. We can see which wavelengths of light there are, separate them out, and say, oh, there must be hydrogen in it because we're seeing these specific wavelengths. And there must be, you know, helium because we're getting these specific wavelengths. And so it's like a signature. Now, the cool part of this we'll have to put off for next week. And that's going to be how we get into the idea of quantum mechanics, and then how we start constructing the atom into orbitals and shells and subshells, eventually to things called electron configurations. All right. So that's all put off for next week.